because now that the consensus is that FP is better, I'm going to tell you how to fix all of your non-FP code. So the inspiration for this talk came from sort of the first half of my career, which I spent deeply rooted in the OO world. I was an enterprise Java programmer, and so everything I wrote was imperative, everything that I dealt with was imperative. And it wasn't until later that I sort of discovered the, yeah?
I can't hear you in the back, so if you can try to stay close to the audio.
Okay. Can you guys hear me in the back now? Yeah, okay. I'll just jog in place. So as I was saying, I didn't get into functional programming until a little later in my career. And so I spent a lot of time at first, once I sort of discovered the joy of it, trying to convert everything in sight, all the imperative code I could find into functional code, mostly because it felt cool. And it was a lot of fun. And I realized that, especially in the code that I wrote, there was a lot of stuff that I didn't know how to convert into functional programming. And over time, by reading blog posts and books and so forth, I started to build up this map in my head of when I encounter this imperative pattern, that's the functional pattern to use if I want to convert the two. So basically I want to be able to answer this question. How do I learn to convert imperative code into functional code? And the mechanism by which I want to do that is functional refactoring. How many of you are familiar with the Fowler book on refactoring? Okay, cool. So I'm basically stealing his definition of refactoring here. The basic idea is to make code, we want to make changes to our code such that it's easier to understand and cheaper to modify, and we'll do that by making it functional. But we'll do it without really changing the code's observable behavior or external shape. And I put a little asterisk around that because we sort of necessarily have to change the types of things, especially if we're encapsulating things in monads or using higher order functions or things. But hopefully the spirit is still the same. The internal behavior of code is still carries the same meaning as it did before. So in this talk, I absolutely won't have time to go over all of these unless I speed talk through the whole thing, which I can do if you want. But what I'll do is I want to give a lot of time for this to sink in, and so I'll go kind of slowly over these examples, and we'll get as far as we get. And then anything I don't get to, I'm totally happy to, if you want to grab me in the hallway or whatever, I can talk about more of these. And then there's even more where this came from, too. I'm also going to pause after each one of these and open it up for questions specific to the refactoring, but please feel free to stop me at any time, especially for those of you who might be less familiar with Scala. I don't want the syntax to impede your understanding of what I'm trying to say. So please stop me and I can reiterate or go deeper into anything that you need. So the first one, I chose this one because dependency injection, is, at least in my world in enterprise Java programming, is a huge pattern. It's all over the place. And it's awful. It's none of these things. It's not clean, especially if you've worked with these frameworks before. You have your configuration sort of scattered about and often written in a non-statically typed way. And because of this, it tends not to yield code that documents itself through types. And it also tends to spin off into this huge, bulky framework that you have to use in addition to the code that you're writing. And for some reason, it presents itself as more than just passing an argument to a function. When we say dependency injection, what we're talking about is taking a function with an input and providing that input. So it actually doesn't need to be as complex as dependency injection makes it seem. So I want to go over an example, and I apologize for the simplicity and contrivedness of this example. I had a much more pragmatic example that I wanted to, a much more realistic example that I wanted to go through, but it ended up being way too big for slides. So as I go through this, try to imagine the dependency, which in this case is going to be pi, as being something like a database connection that gets injected by your dependency injection framework. So what we're going to do is compute cylindrical volume. So first we have to write a function to calculate area, which we have there, pretty simple. And then we'll write a function to calculate volume. So we take our area function, which gives us the area of a circle, and we just multiply that by the height of the cylinder, and we get the volume of the cylinder. And so right away, we can see, we can start to smell the need for dependency injection, right? We have this volume function. It takes 3 arguments, pi, radius, and height, but it doesn't actually use 2 of those 3 arguments. It doesn't use pi and it doesn't use radius, other than the fact that it passes them along to this other function that it's calling. So this is really frustrating, and you can imagine that in a larger program, especially one where database connections are involved, for example, there will be lots of these deep call stacks where functions are taking arguments for the sole reason of passing them along to other function calls. So that's a drag, and that's something that we can fix with the reader monad. Normally, I would probably reach to a library like Scala Z or cats for a reader, but I wanted to show the shape of what it looks like. I mean, it's actually simple enough that we can fit it on one slide. So the basic idea of a reader is it's a data structure that wraps around a simple function and then gives us some combinators, and that's it. So here we call reader a class that wraps a run function. So it has a single field called run, and run is a function from E to A. And the reason for those letters is somewhat arbitrary, but you can think of a function with a dependency as a function that needs an external environment, and that's what the E sort of represents. So run is a function that, given an environment, can execute and return some value of type A for any arbitrary value, or any arbitrary type. Additionally, we get these 2 combinators. Really, all we need is flat map. We could implement map using flat map, but it's a little bit more optimal to do it this way. And I won't go too deep into the implementations of these, but the key idea is to just look at the types of these functions, of these methods. So if we have, let me use my pointer here. So given, can you guys still hear me in the back if I walk over here without the mic? Cool. All right, so if we have a run function, and that's a function that we want to represent as a function with a dependency.
The recording can't hear you though.
Oh, the recording? Oh, drag.
It can, the mic is down there.
I'm sorry.
Yes, we can hear you.
So I'm okay over here?
Yeah.
Cool. The laser's easy to point with in the cursor. Okay, so we've got our function here that is a function with an external dependency E. After that function runs, once it has that dependency, once we've injected it, we get an A. And there are lots of things we might do with that A. We might just pass that A along to another function that converts it to a simple B, in which case we would use map. Or we might take that A and pass it to a function that produces yet another reader, another dependency that, a dependent function that depends on that E, for that. I'm not going to go too much into detail on these, but this pattern will come up over and over. And if you want me to go back to it at any point in the next few slides, feel free to let me know. So let's refactor this thing. The first step in refactoring is to extract pi as a dependency. The idea is we don't want pi to be an argument that we have to supply to the volume function in particular, but while we're at it, we'll do the same to the area function. So we comment out our old area function, and we drop the pi argument completely. So now area is a function of a single argument, radius, and that returns a reader. So that says, I'm going to return a data structure that wraps a function that has a dependency on pi. So you can run me when you've got pi, and then I will compute the area and return that. So this is sort of like a continuation. It's a function that has yet to run, because we don't yet have our dependency. Now pi is a pretty easy dependency to conjure up, but again, if you think of something more like a database connection, that's something that we have to wait until later. Okay, so also part of step 1 is updating the volume function. So we're going to comment out the old one, and once again, we're going to drop that pi argument, and we're going to move it down into the reader. So this one's a little bit different. We're not constructing a reader like we did with the area function. Instead, we're going to use map. So what we do is we have radius and height. Those are arguments to our new volume function. So we call area R, which we had on the previous slide. Dope. Right. So when we call area R and we provide a radius, it gives us back a reader. And check out the type of this reader. It says it's a reader double double. So it's a reader that takes an environment that's a double, that's pi. and it returns a double, that's the area. So this will give us our reader. Now that we have a reader, that's a reader that takes pi and gives area. We want to do something else with that area, so we use map. Map says, you give me a function that does something with area and returns something, and I'll give you a new reader that, given pi, returns that new thing. So we simply map area into a function that multiplies by height, and we've got volume. So this whole thing itself returns a reader. We still haven't actually done any computation because we don't have pi yet. So this returns a reader, a reader double-double. So it's a reader that takes pi, which is a double, does a bunch of computation, and returns volume, which is a double. And this is how we'd use it. So we call our volume function. We provide radius and height, and that returns our reader. So now we have our reader. It's ready to go as soon as we have pi. We have pi there, roughly. So all we need to do is get the run function out of the reader and apply it with the single argument, which is pi. So when we run this, it returns a double. It returns the volume of the cylinder, which is 700 something. But we're not done yet. If I go back a slide, when we dropped pi from volume, I said it was because volume doesn't actually really use pi other than it's passing it along. But that's the same is true for radius. Volume, the way I've implemented volume, it doesn't actually care about radius. So let's repeat this process and get rid of radius as an argument. So we're actually going to have two dependencies that we're going to inject. So like before, we'll start with area. We don't have to, but it's kind of neat to see both of these converted to readers. So the first thing we do is drop the argument. We no longer have a radius argument. And because of that, this area function no longer even needs to be a function. It's just a value. It never changes. The type is quite a bit more complex, so let's step through it. The way you would read this is area RR is a reader that takes an environment which is an integer, and that's our radius. And once we provide it with that radius, it returns a value that is itself a reader. So that's another thing that has another dependency. So that thing has a dependency, which is a double, and that's pi. When we supply that thing with pi, it will finally give us a value that is a type double, and that's the area that we're looking for. And the way we build this thing up is we construct a new reader that takes radius, and it returns a new reader that takes pi and returns the area. And then the same kind of thing as before, we want to drop the radius argument from our volume function. We can't make this one a val because it still depends on a height argument, but it at least doesn't have any more pi or radius arguments, which is nice. So this thing returns the same type of area. It's a reader that depends on the radius, and returns a reader that depends on pi, and finally returns a volume in this case. And again, we're going to use our area function and map on top of that. Yeah?
I had a question over here and one down there.
Oh, sure. Questions? Yeah?
What is the advantage of using reader over carried functions that take the environment as the last one?
Yeah, that's a really good question. So the question is, why are we using this reader thing instead of just using functions and composing functions together? The glib answer is there's no reason. You could absolutely do that, and it would be much cleaner. But practically speaking, that we wouldn't get map and flat map if we were just dealing in functions, unless we did some kind of ad hoc polymorphism where we can go from a function to something that can map and flat map other functions. But philosophically, you're right. All we're really doing is composing functions together. We're just using reader because it gives us a little bit of clarity in the type, and it gives us these extras that we've built into the reader class. Is there another question?
You covered it.
Cool. Okay, so area RR, which we had on the previous slide, gives us a reader of the same type. That given a radius and given a pi gives us an area. So if we call map, that gives us access to that reader that's inside of area RR. And on that reader, if we call map again, it'll give us access to area, which we just multiply by height. And then this whole thing becomes one giant double reader, which will eventually return volume. And so to use this, it's basically just like before, except now we have two readers to run. We've got two dependencies to inject. So when I call the first volume RR, it returns that reader into reader double double. I apply it with 6, and that will give me an inside reader, the reader double double, which I then apply with 3.14, and this will give me my final volume, which is a double. Okay, so that's it for this example. You have to sort of stretch your mind, I guess, and imagine a much more complex real-world example. But this pattern, especially when we start using for comprehensions and other combinators, this pattern will pay off immensely when you want to eliminate these unnecessary arguments or when you want to sort of push them to the edges of the evaluation of your program. Yeah?
Do I just have to know what order to pass the doubles in?
Right, so...
Because if I flip those, because there's no way of telling you which one to pass in first.
Yeah, that's a great question. How do we know that we do run 6, run 3.14 instead of the other way around? In this case, it's a little tricky. The first dependency is an int, and the second is a double,
Okay.
So that'll tell you a little bit. But, yeah, but what if they were both doubles, and we wouldn't be able to tell them apart? And so I don't have one answer to that. There are different approaches. You could use new types to make a discrete type for every single dependency that you might have.
Okay.
That's one way. It gets annoying to manage all those types, of course. Or you could have one sort of huge configuration object that has all of your dependencies in it. And then rather than having these nested readers, you just have one reader that depends on this big configuration object.
Wouldn't that look a lot like your dependency injection?
Yeah, then it looks just like dependency injection. So, I mean, it's not a bad approach necessarily, but now instead of having these very nice specific implementations, like area depends just on pi, this would become something that depends on your big configuration object, and then it would have to know how to pull pi out of that. So it's kind of a drag. There are other things you can do, like end up with these nested readers and then build an interpreter that iteratively evaluates that nesting. And then if you use something like a free monad, you can decide if there's more work to do or if you're done based on the type of the thing that's returned. That's way out of scope of this talk, though. But yeah, it's definitely a tricky problem to try to tackle. Okay, any other questions on this pattern? Cool. All right, so we have a few more minutes. I'll try to tackle one more. Okay. So I think I have a bug in my slides. The next one is replacing exceptions with sometimes. So exceptions are, exceptions are interesting because if you're using checked exceptions, they're maybe not that terrible because you can look at the type of a function and you know that it might return a value or it might throw an exception. But you don't always have checked exceptions. Sometimes they're unchecked and exceptions can be thrown and totally surprise you because the type of the function did not give you any kind of clue that that was going to happen. But either way, they're not super clean. You have to have TryCatches and you have to decide what to do in the case of an exception, what kind of a default value to return, for example. And so we want to get rid of them. So here's a really simple example, integer division. If we divide by 0, of course, we'll throw an exception. So to use this thing, while being resistant to that exception, we have to use a TryCatch. And that's annoying, especially if we want to return an int. So if I want to calculate the quotient of this and expect the value to be an integer, in my catch statement, I have to come up with some default value to return in the case that an exception was thrown. And that's terrible because 42 divided by 0 is not negative 999. But what else can we do? So here's what we can do. We can use a sum type. And the sum type, I think I'm using that term correctly, but basically it means that we're going to have one of a set number of possible data types. And in this case, we're going to use either. Once again, either is already in the Scala standard library, and it's in lots of other libraries, but I wanted to sort of spell it out so we could understand what we're looking at. So when a function returns an either, in this case, it's going to be one of these two values. And conventionally, we use left to encapsulate errors and right to encapsulate successful values, but that's arbitrary. You can pick whatever convention or naming scheme you like. So to refactor this thing, we get rid of that old exception throwing division, and we still use our TryCatch, but this time we're building it into our division function. And rather than returning an integer, we're returning an either of an exception or int. And so the idea is we try to do a division. If it succeeds, we put that inside of a right. If it fails, we put that inside of a left. And either way, we're returning some concrete value that is one of the two kinds of either's.
Why is the right in?
What's that?
Why does right match the signature?
So this returns an either of exception int. And the way we declared right, so right AB is an either AB, where the value inside of the right is of type B, or whatever B. So our A and our B are exception or int. So a right of exception int is an either of exception int. And similarly, a left of exception int, which has an exception in it, is also the same type. So if we make our function return an either of exception int, then we can return a right of int or a left of exception.
In that case, wouldn't you just want to use a try?
Yeah, Scala has try, which lets you, I haven't used try a lot, but I think you would declare it as def div e returns try of int. Is that right? Yeah, so I think if I understand try correctly, it's this specific case of either where it will be a value or an exception.
Right.
Yeah, exactly. But there might be other things that you want to capture in your left rather than just the raw exception.
Could you just use an option there and just
Yep.
turn it on if it's the exception?
Yeah, you could use an option. The problem with option is your error case would be a none, which doesn't really carry any interesting information. So there's nothing wrong with that, but you might want that information for other reasons, debugging or logging or something. Okay, so now to use this thing, we call it, we pass it our failing division 42 divided by 0, and we don't have to worry about TryCatch. We know that the result of this will be a left or will be a right, and in this case it's a left of some arithmetic exception that Java throws. Okay, so far that's fine, but it's actually not composable because we haven't made it monadic yet. So we can do that by biasing our either to the right. I don't have time to get into why we can't write an apple flat map for both left and right. But when we want to compose a bunch of these things in like a for comprehension, for example, we need basically a single default map and flat map that will work whether it's a left or a right. And so in this case, I'm doing that with this implicit class. So this says if I've got an either, and so that could be a left or a right, and on that either I call either flat map or map, then we'll use this implementation. And so if we're in a flat map or a map, like if we're using a for comprehension, and we're talking about a left, because this is a right bias either, we're assuming that there's nothing we can do. So the only thing, so if we have a left, we have some error, which means we can't continue to do anything interesting with the data because we haven't data. So all we do is return that same left. If instead we have a right, that means we have a right of a B, and so our flat map is looking for that B, and it's going to return some new either. So all we have to do is run F on the B that's in the right, and then map is similar. We're just implementing it using flat map. So I just have a couple minutes. I'd like to show how to use this thing. And so the reason that this is useful is you can now chain together lots of things that could potentially blow up without having to worry about anything blowing up. So what this will do is it will attempt to divide 42 by 7, and the result of that will be a right of 6. And using this syntax, we can bind that 6 to this A, and then we continue. And so we try to divide 6 by 0. That won't work, so that will give us a left. And then when we try to bind this B to the right, it can't happen because in our flat map we have a left, so we just return a left. So actually this third line simply will not run. And the output of this whole expression will be a left of the exception that happened here. And so this is nice because we can very safely do a whole bunch of, well, we can write our code such that it's doing a whole bunch of sequential operations, each of which could cause the rest to fail. And if any of them fail, we end up with that failure at the end of this thing, rather than like a thrown exception that we have to catch. Any questions on exception to some type? Yeah.
Sorry, if you go back to the last slide, did we, what it returns an either?
Yep.
And then what is the first argument to Divi? Is of type?
The first argument to what?
Divi's first argument must be of type.
Integer.
But if Divi returns an either, then A is an either, and Divi takes
Ah,
either.
right. So this is just Scala's syntax sugar for using map and flat map. So A is not the return value of div E.
Okay.
You're right, div E returns an either, not an int, and we're using A as an int here. So when we use that syntax in that for comprehension, A represents the input to this function. So since B is int in our either exception int, B has the type int. And so when we call flat map, which Scala will desugar this into 3 flat maps and a map.
Well, that is syntactic.
Yeah, so Scala will basically turn this into div E427 dot flat map of a function A to all the rest of this. And so when we say dot flat map of a function A to something, that function is this guy right here. And so that's the function that can't run if we have a left, because if we have a left, we don't do anything with that function. We're just done. Any other questions? Yeah.
You mentioned that check exceptions are nice because you're forced to handle them normally, and that this is better for catching unchecked exceptions. But how would you go about finding them in the first place? Like either you come across runtime errors, right, and then you refactor that specific function to return either, or you proactively write every single function in your entire code base to return either, because you have no idea whether it will
Right.
return.
Yeah, I haven't solved that one yet. The question is this, at first I talked about checked versus unchecked, and checked you know because it's part of the type, unchecked you don't. This doesn't solve the problem of discovery of functions that can throw unchecked exceptions. So you can go crazy and basically wrap every single function call in this thing, which I've tried. I've tried writing in FFI for Java libraries, and everything is an either exception option of that value that's supposed to be returned. But in practice, that's super annoying. I wouldn't recommend it. Yeah.
Yeah, wouldn't it be, well, isn't it sad that we cannot do stuff in parallel? Like, suppose C is bad and A is bad, just compose, make it applicative function, this right vibes, turn it into validation.
Yep, so these are all very monad focused, and monads are necessarily sequential. But you're right, we could do similar things, similar refactorings, which I don't have in this slide deck, for like, validation. And validation is nice because you don't have to wait for this thing to finish to do this one, because they're necessarily independent of each other with applicable validation. That's not the case here. But in those cases, yeah, it's cool because you can parallelize it.
And you can accumulate errors, right?
What's that?
With validation, you can accumulate all the errors.
Okay, so that's all the time I've got. There's a lot more interesting stuff here, so feel free to grab me afterward and I can walk you guys through it.